Hey guys, my name is Jonathan Lopez. I will be your math teacher for today. You can call me Mr. Al or Mr. Lopez. I'm cool with whatever. Let's get right into an assessment test question. A new prototype set of carbon fiber bicycles wheels with a diameter of 27 inches are being tested by professional cyclists by riding them down a steep hill as fast as they can. It was observed that the highest revolutions per minute that the wheels achieved during the test was 675. I highlighted some two key phrases that we are definitely going to need: a diameter of 27 inches and revolution per minute being 675. The first question is, what is the angular speed of the wheel in degrees per minute when the wheel reached the highest RPM during the test? So we know that the angular speed equation is central angle over time, central angle being 675 revolutions per minute, because the central angle is either in degrees or radians. And the reason why it is in degrees for this instance is because there's 360 degrees in one revolution, because the definition of a revolution is a full rotation around the circle. And we all know that a full rotation around the circle is 360 degrees. The time being 1 minute, since we are talking about degrees and minutes, degrees per minute. Knowing that there's 675 revolutions and knowing that there's 360 degrees in one revolution, we can multiply that to get our degrees, and that is 243,000 under 1 minute. In 1 minute, of course, since we are talking per minute. Continuing with test question B, according to the computer simulation, the wheels could become unstable and cause the bike to go into a high-speed wobble if the wheel reaches a speed of 55 miles per hour. Were the professional cyclists at risk of experiencing a high-speed wobble when testing the new wheel on the downhill? Reference your work to justify your answer. There are two things that I highlighted here, that being speed of 55 miles per hour, so that is the speed that we're comparing to, and at risk of experiencing a high-speed wobble. Now that's what we're trying to figure out. Now, going back to the info that we got from number one, diameter is equal to 27. The reason for that is diameter. The diameter means from one side to the other side of the circle, which is like the total space between those two. Now, what we want to do for the radius is we want to cut it in half, because the radius starts from the center of the circle to the edge of the circle and ends to the edge of the circle. So logically speaking, we could split that to get our radius, and that's exactly what we did here. We did that, and we got 13.5 as our radius. Now, the reason why we are bringing back 675 revolutions to this equation is because 675 tells us the distance that the wheel rotated under 1 minute. And we are multiplying it by 2 pi because we are doing a linear speed equation, which means we have to use radians instead of degrees. And we have to also multiply it by the radius to actually get us an actual distance factor for this one. Now, we can divide it by 63,360 inches, since there is 63,360 inches in 1 mile, and we're trying to figure out miles per hour, so our outcome would be 0.90365 under 1 minute. Now, since we know that there's 0.90365 under 1 minute, we want to figure out hours, which means we have to look for outside thinking. That outside thinking being that there is 60 minutes in 1 hour. So logically speaking, we can multiply that by 0.90365 and get us approximately 54.22. Now, when comparing the speeds, 54.22 miles per hour does not equal 55 miles per hour.